Thanks for tuning in. I'm Benjamin, and currently I work at Dropbox. And I'm here to tell you about a set of Bazel rules we at Dropbox have developed for Python over the last 5 years. Firstly, though, why did we build our own rule set for Python? A cursory inspection of the Bazel documentation reveals that Bazel already has Python rules built in, so why don't we just use those? Unfortunately, Bazel's built-in rules are limited. They assume a Python interpreter is already installed somewhere on the system, which compromises hermeticity. Bazel does not support compilation of bytecode cache files, PYCs. Having bytecode cache files around is not essential for running Python, but it helps the startup time of large applications. Perhaps the severest problem of the built-in Python rules relate to third-party dependencies. Bazel has no built-in way to build C extensions. It doesn't understand wheels, a common Python packaging format, or how to download dependencies from PyPI, the Python packaging index. These shortcomings lead to the conclusion that Bazel's built-in Python rules are only suitable for trivial use cases and Google. I'd note that Blaze's Python rules do not suffer from most of the defects that I've enumerated in Bazel's. However, Google's Python practices evolved years ago and have drifted far from how most Python is developed today. So Blaze's Python rules are not directly useful outside of Google, which explains why they have not been open sourced. Dropbox needed Python rules for Bazel before the advent of the open source and semi-official rules Python set. So we needed to strike out our own to create production-grade Python rules. Even today, our Python rules provide some unique features over other Python rule sets like rules Python. Our Python rules are part of DBX build tools, a collection of rules and tools related to Bazel that Dropbox has developed over the last 5 years. It is used heavily internally for millions of lines of Python in production. The source is available on GitHub at the link in this slide. As is implied in its name, DBX build tools contains more than just Python rules. And we've given talks at previous Bazelcons about some of the other tools in DBX build tools. In 2017, we talked about our integration testing framework built with Bazel. And in 2018, we talked about our build file generator, which can automatically generate dependencies from source files. As we'll see later in this talk, the generator can also be applied to Python and works with our Python rules. Let's first take a look at how our Python rules look to the user, that is, people writing build files and Python code. The macro structure of our Python rules will be familiar to anyone who has used the built-in Python rules, or indeed any language rule set. Bazel's built-in Python rules generally have counterparts in our rule set prefixed with dbx_. To access them, a build file must load from the @dbxbuildtools workspace. The most common rule, dbxPyLibrary, describes a set of Python sources, possibly with some dependencies, for other code to import. In the example in this slide, mylib contains one source file, mylib.py, and mylib depends on another dbxpy binary library rule, barlib, in the foo package. The dbxpy binary rule creates an executable that invokes the script listed in its main attribute. With the code on this slide, running the myapp target after it's built will execute the code in myapp.py. Myapp.py may itself import from mylib since the binary rule has a dependency on the mylib rule. There is, of course, also support for testing in our rule set. The simplest kind of test uses the dbxpy test rule, which is a dbxpy binary marked as a Bazel test rule. This provides the most general kind of testing Bazel supports. If the binary exits with status code 0, the test passes, otherwise it fails. Bazel collects whatever logs the binary prints into the test log. This simple rule is useful for oddball tests and wrapping third-party test cases. For most of our tests, though, we want some more structure. In the Python world, Pytest is a very popular test runner, and we use Pytest heavily internally at Dropbox. Our Python rules have special support for Pytest in the form of the dbxpy Pytest test rule. Try saying that 5 times fast. This rule runs Pytest to collect and execute the tests in its sources attribute. The wide penetration of Pytest in the open source world means Python programmers can use dbx PyPI Pytest test without learning new conventions. Since it is more structured, dbx Pytest test automatically supports richer integration with Bazel. The rule automatically produces XML test result output in JUnit format. It also has native support for some special Bazel test command line flags. --test filter for running individual tests within a test target from the command line, and --test runner fail fast, which makes test targets fail as soon as one individual test case does. The next topic I'll discuss is how the Python rules integrate with third-party libraries. But first, let's touch on the challenges in integrating the Python ecosystem with Bazel. A central issue in Python packaging is that the native packaging system is based on arbitrary code execution. Python source distributions have a file called setup.py that is invoked to build a package. Most packages setup.py files call into distutils, a venerable library of helper code for packaging in the standard library, or they call into its equally venerable counterpart, setuptools, which is a third-party package. This fact means that there's no universal declarative way to discover the dependencies or other build metadata about a package. You have to execute setup.py to do basically anything. Furthermore, setup.pys frequently do feature detection by probing the system. So we must figure out a way to tame arbitrary packages into producing hermetic archives during the build. As an aside, I can note that the Python packaging situation is improving every day. Many dedicated people have been working in the Python packaging ecosystem in the last decade, and a lot of progress has been made. Unfortunately for package consumers, life is as tough as your thorniest third-party dependency. And in my experience, large code bases always seem to need at least one really old third-party dependency with a wicked homegrown build system. Here's an example of how the dbx build tools rules integrate with external packages. The main rule we use is called dbx PyPI piplib. That rule pulls in a dependency from the Python package index. That's what PyPI stands for in the rule name. 6 here is a simple library, so we only need to provide the library name and version. Traditionally, we put our third-party library rules in subdirectories of a pip directory at the root of a repository. This aids discoverability for humans and tools. Once a piplib rule like this is set up, first-party code can depend on it as if it was a normal dbx py library. The imports just work out for the calling code. Of course, not all of the Python ecosystem is simple one-line pure Python libraries like 6. Python dateutil furnishes a more complex example. The name and pip version attributes are still here, but some other information has come into play too. The first thing to notice is that Python dateutil has a dependency on 6. Such inter-PyPI dependencies are declared using the deps attribute of dbx PyPI piplib. Python dateutil also has a setup requires dependency on setuptool skim. That means setuptool skim is a build time dependency of Python dateutil, so it must be present when Python dateutil is being built. However, setuptool skim does not need to be around at runtime when Python dateutil is imported. This Python dateutil rule also has a provides attribute. The provides attribute declares what names the code is importable under. Python-dateutils is the name of the package on PyPI, but the dependent code loads it under the dateutils name. Provides is a list because some packages occupy multiple namespaces. For instance, setuptools, the package, provides code both under the setuptools and package resources namespaces. A related feature that we also support is namespace packages, which is new in Python 3. In namespace packages, multiple packages may contribute code to the same top-level package. For example, many separate packages for Google APIs are importable under the Google top-level name. Unfortunately, the dynamicness of Python packaging, which I discussed earlier, means that the data that goes into these attributes is not readily available anywhere in a declarative fashion. Normally, figuring out the right attribute values is a manual process that involves some code inspection of the package. We've gotten quite good at turning setup piles into proper dbx PyPI piplib rules at Dropbox. Our third-party Python rules also have transparent support for linking to native dependencies, like C or C++. For example, here is the build file for the cryptography package. The cryptography package uses OpenSSL, and the cryptography build file indicates the dependency by putting the target for the rule that builds OpenSSL into the deps attribute of the cryptography package rule. Here, at org OpenSSL //:SSL is a CC library rule that the Python rules transparently know how to link into the build products of cryptography. Sometimes a third-party package needs to be forked, either because it can't be built unmodified or some other patching requirement unrelated to the build system. DBX Build Tools natively supports forking third-party code into the source tree. The example on this slide builds a local version of the Django web framework. We've copied Django into the third-party /Django directory, made desired modifications, and written a dbxpy local piplib rule in the build file. A dbxpy local piplib is very similar to the dbxpy pi piplib rule seen earlier, but it builds a package from the files in the sources attribute rather than downloading the sources from the internet. The pip version attribute is still used, but only serves a documentation and auditing purpose now because nothing is downloaded from the Python packaging index. One of the more useful features in DBX build tools for Python is build file generation. I won't venture deeply into the mechanics of build file generation since, as I said at the beginning of the talk, we gave a whole other talk about it at Bazelcon 2018. The main feature of the build file generator is writing dependencies in build files based on import statements in the source code. The build file generator can infer dependencies on libraries in the same package, different packages, as well as third-party dependencies in the pip or third-party directories. These different kinds of dependencies are seen in this generated example. A few other extra features of our rules are worth briefly noting. Firstly, we have a verifier in the form of a command line aspect for library rule dependencies. The verifier checks that library rules directly depend on all the libraries they import, and conversely, they don't depend on any libraries they don't use. Users don't run afoul of this verifier very frequently because of automatic build file generation, but the system is still useful as an independent check on the build file generator and also for manually written library rules, which happen sometimes. Secondly, we support having binaries that run Python 2 and binaries that run Python 3 in the same build. If you're lucky enough to not have Python 2 in your codebase, you won't care about this. But for codebases transitioning between Python 2 and Python 3, it's invaluable to be able to build code using both versions. In theory, this Python 2 and 3 support could also be extended to arbitrary Python versions. For example, we could allow running Python 3.8 and 3.9 in the same build. It's quite possible that we will delete this support for multiple versions from DBX build tools once we manage to get rid of Python 2 in our code base because a feature adds a lot of complexity. Next, I will touch on a little bit how the rules work internally, their guts. The crux of the DBX build tools Python rules is dbxpy binary. That's because it brings together all transitive Python code, first and third party, into a working executable. Building a dbxpy binary produces several items into the executable's run files tree. First of all, there's the executable's code, including .py files from transitive library rules. PYC bytecode cache files are also generated into the run files tree for all .py files. Second of all, there's the third-party code from dbxpy PyPI piplib and dbxpy local piplib rules. Third-party code is built and unpacked into the run files tree, so it can be imported by Python. Third, there's a hermetic Python interpreter with its standard library. We build a Python interpreter so that it has all of its third-party dependencies statically linked in, except for libc. This yields portability and reproducibility across a wide range of Linux systems and distributions. Finally, there's a wrapper shell script named after the target that invokes the hermetic Python with the right Python path environmental variable and leaps into the user's main code. This layout means the dbxpy binary's run files tree can be copied to almost any Linux system and run without installing other dependencies. That's very helpful for distribution. Now, a peek into the grimy third-party packaging build process. The basic idea is to, for each package, invoke pip, the Python package builder and manager, in a controlled environment so it produces what we need using only the dependencies that have been declared. Bazel's Linux sandbox helps greatly with this task. Within the sandbox, we build a little virtual environment for pip, install the target package into it, and finally produce a wheel of the built package as the ultimate output of the rule. Native dependencies are especially tricky because most packages are expected to be able to probe the system for headers and libraries to compile and link against. But we want packages to only use the code and dependencies that we provide. Both native dependencies and the need for determinism require a lot of delicate code. We might just say hacks. For example, we need extra compiler and pip flags to ensure absolute paths aren't written into the build artifacts. We provide a wrapper for the linker to ensure that undesired system libraries are not linked. Overall, there's years of accreted hard-won knowledge about building Python packages in our code for this. And I'm sad to say that I know things like how to configure NumPy so that it accepts a hermetic Fortran compiler and runtime. The DBX build tools Python rules assume conventions that do not universally hold in the Python world, so the rules may not easily work out of the box for everyone. A primary expectation of our rules is that there is only one entry on the Python path within the main workspace. That is to say, all Python imports are resolved from the root of our repository. This rule makes it easier for humans and tools to find Python code corresponding to imports. A very important tool that wants to match imports to source files is the build file generator I talked about earlier. So previous to using Bazel, Dropbox had a more complex Python layout in our repository. And in order to achieve the structure of only having one entry in the Python path, we had to move a lot of code around. But we're really glad we did it, though, because it really helps with clarity in the code base. Another assumption of our rules is that there will be only one version of a third-party dependency in our tree at a time. Again, this is partially to support build file generation, because if there's only one version of a third-party package, there's no ambiguity in resolving imports to it. This so-called one version policy also has merits on its own. It prevents diamond dependencies from arising, and it makes auditing for security issues easier. Lastly, we prefer to build third-party packages from source. This gives us control over dependency versions and ensures we are never stuck with a binary blob that doesn't work on a newer operating system or compiler. It's more work up front, definitely, to compile from source, but the peace of mind it produces is worthwhile in our view and experience. So there exist workarounds available to subvert all these guidelines, but our Python rules are definitely streamlined for code bases that conform to these suggestions. The DBX build tools Python rules have been stable for several years now under heavy use. But as it is the way with software, there are improvements to be made and bugs to be fixed. Let's discuss a few. Firstly, we could use better cross-platform support. Our rules have had the most battle testing, and we've had the most experience using them on server-side Linux. In the last year, we began working on supporting macOS and Windows, primarily for our client applications, but there's a lot more work to do to bring them to parity with Linux. In particular, we don't support hermetic Python interpreters on Windows or macOS. Secondly, we'd like to explore other distribution mechanisms for binaries. The self-contained run files tree with a hermetic Python interpreter works fairly well on server-side Linux, but a single file executable could be better for other operating systems and distribution channels. A major difficulty here is a lot of Python code, both first and third party, assumes it is installed directly on a file system. Lastly, there are upcoming challenges in the Python ecosystem. Historically, Python packages have done all their building through distutils, or as third-party replacement setup tools. Distutils and setup tools have had long-standing problems, so recently Python packaging tools gained the ability to use completely different build backends, using a system introduced by PEP 517. DBX build tools today is somewhat tied to distutils and setup tools implementation details. For example, it's quite subtle and delicate task to inject the right compiler and linker flags into them. Our Python rules in the future will need to ensure that packages using new build backends can be built as easily and hermetically as distutils project. This may be particularly hard if new build backends don't provide the same configuration knobs as distutils and setup tools. And that's all. Thank you very much for listening and your attention. Again, here's a link to the DBX Build Tools project on GitHub, and we're looking forward to your feedback.